Okay, so get this right. A miniature robot that swims, and I mean miniature, like just a few centimeters long.
Oh, why?
This thing is zipping around on the surface of the water.
Yeah.
Incredible, really, what they've packed in to such a small
It
package.
really is quite remarkable.
So it's modeled after marine flatworms.
Right. So,
Super flat creatures.
those super flat creatures, yeah?
Yeah, and they move with a kind of undulating motion.
Yeah, and they applied that to the robot's design.
And they're using
Cutting-edge
soft robotics technology.
soft robotics technology, exactly.
So it's tiny and it moves like a flatworm. What else makes this little swimmer so special?
Well, for starters,
Yeah.
think about a flatworm gliding through water. It's effortless, right?
Yeah.
This robot mimics that using a pair of soft, undulating pectoral fins
Okay.
for propulsion.
Mm.
And the real genius is in how they've powered and controlled this tiny machine.
Let me guess. Tiny batteries, microchip brain.
You're getting close.
Close. Okay.
They've actually managed to fit a miniaturized high-voltage power supply
Wow.
and a tiny onboard computer,
Mm.
all onto a circuit board, smaller than your fingernail.
Whoa.
It's mind-boggling as they miniaturized everything.
So it's not just a tiny robot. It's a tiny high-tech robot. What about its weight? All that tech, it's got to add up.
Surprisingly, no.
No.
The whole thing weighs less than 7 grams.
Mm.
It's so light that it actually floats on the surface tension of the water.
Wow, that's amazing. It's like they've managed to defy physics to create this tiny, powerful swimmer.
Yeah.
I am really curious about these actuators you mentioned earlier.
Yeah.
What are they and how they work?
So the actuators are the muscles of this robot. They're the components that make those fins move.
Okay.
These are special, soft, electro-hydraulic actuators.
Okay.
They work by using an electric field to squeeze a liquid dielectric.
Mm.
Imagine like a tiny balloon filled with liquid.
Okay.
When you squeeze it, it changes shape. That's essentially what's happening here,
Okay.
causing the actuator to bend and move the fin.
So they're using electricity to control fluid pressure to create movement?
Yeah,
That's pretty ingenious.
it is, and they didn't stop there.
They didn't stop there.
They even experimented with a special type of polymer in the actuators.
A polymer, like plastic?
Exactly, like plastic.
Okay.
This particular polymer allows the actuators to operate at much lower voltages.
Why is that important?
So lowering the voltage makes the whole system more energy efficient,
Mm.
which is crucial when you have such a small power source.
Yeah, that makes sense.
It's a delicate balance
Mhm.
between packing in enough power to make the robot move
Right.
and making sure it can actually operate for a reasonable amount of time.
So we've got a tiny, lightweight robot with efficient actuators inspired by flatworms. What kind of performance can this little guy actually achieve?
Well, hold on to your hat, because this is where things get really impressive. This tiny bot can reach speeds of over 5 centimeters per second.
5 centimeters per second doesn't sound like much.
It might not sound like much,
Yeah.
but that's like a human swimming the length of an Olympic pool in under a minute.
Okay, now that puts it into perspective. So it's fast. What about maneuverability? Can it turn easily?
It's not just fast, it's incredibly agile.
Hmm.
We're talking about turning almost on the spot
Wow.
at speeds up to 195 degrees per second.
Wow, that's incredible.
That's faster than most fish can manage.
Yeah.
And remember, those individually controlled fins,
Yeah.
they give the robot a wide range of motion,
Mm-hmm.
forward, backward, sideways, turning on a dime.
Turning on to that, it's like a tiny aquatic sports car.
Exactly. Navigating a dense rice field
Mm.
effortlessly, weaving through the stalks.
Wow.
That's the kind of environment the researchers had in mind when they were designing this robot.
So it's nimble, it's fast, it's efficient. What else can this little robot do?
Well, besides being able to control it remotely,
Yeah.
they also managed to create a completely self-contained system.
Hmm.
This means the robot doesn't need any external power or control.
Wow.
It's free to explore on its own.
That's amazing. So it's truly autonomous. So they
Right.
just set it loose and let it roam around.
Not quite.
Not quite.
They've demonstrated its ability to be remote controlled,
Okay.
navigating it through obstacles, and even having it push objects much larger and heavier than itself.
Wow. That's incredible. So it's strong too.
Deceptively strong,
Yeah.
but they didn't stop at remote control.
They didn't stop there. Okay.
Remember those phototransistors?
Yeah, they were part of the onboard electronics, right?
Right. Well, these phototransistors allow the robot to sense light.
Okay.
They basically give it rudimentary vision,
Oh.
so it can follow a light source
Yeah.
autonomously.
So that's like giving this little robot a mind of its own.
Right. It's pretty remarkable.
They literally gave it away to see. Wow, that opens up so many possibilities.
Yeah, it does.
What stood out to you most in all of this research?
For me, it's the sheer ingenuity of it all.
Yeah.
They've managed to pack so much functionality into such a small package. The miniaturization,
Yeah.
the agility,
Yeah.
the autonomous operation. It's like they've taken everything we know about robotics and condensed it into this tiny, remarkable machine.
I have to agree. It's mind-blowing to think about what they've accomplished.
Yeah.
We've only just scratched the surface of what this little robot can do.
Right.
What are your thoughts on the potential applications of this technology?
The possibilities are truly vast.
Okay.
Just imagine these tiny robots monitoring water quality, exploring delicate ecosystems,
Yeah.
even assisting with search and rescue operations.
It's incredible to think about the impact this little robot could have
Right.
on so many different fields.
Yeah.
And it all started with a simple flatworm.
Exactly. Sometimes the most groundbreaking innovations come from the most unexpected sources.
This has been an incredible start to our depth dive.
Yeah, for sure.
I'm already hooked.
I'm excited to see where we go from here.
Yeah.
There's still so much to explore.
Absolutely.
Yeah.
Welcome back to our deep dive.
Yeah.
We just finished talking about how amazing this tiny robot is.
Right.
I'm guessing it wasn't all smooth sailing for the researchers, was it?
You're absolutely right.
Building something this advanced
Yeah.
must have come with some serious challenges.
Creating something this groundbreaking is
Yeah.
never easy.
Yeah.
In fact, one of the biggest hurdles they faced was figuring out how to power those tiny actuators.
Yeah.
Remember we talked about how they use an electric field to squeeze a liquid?
Right.
It requires a pretty high voltage.
Yeah, I remember you saying it was hundreds of volts. It's hard to imagine squeezing that kind of power onto a circuit board
Right.
the size of a fingernail.
Exactly. Not only did they have to miniaturize the power supply itself,
Right.
but they also had to make sure it was lightweight enough
Yeah.
for the robot to stay afloat.
To stay afloat, yeah.
A real balancing act.
So how did they manage to solve this power puzzle?
They had to get really creative.
Okay.
They ended up designing a miniaturized open-loop flyback converter circuit. Imagine a super efficient voltage booster.
Okay. So they took the relatively low voltage from the onboard battery
Yeah.
and boosted it up to the hundreds of volts needed for the actuators?
Precisely.
Wow.
And they did it all while keeping the power consumption as low as possible. It's a remarkable feat of engineering.
Yeah.
They didn't just cram things in and
Yeah.
hope for the best.
Yeah.
They really had to think outside the box,
Yeah.
push the boundaries of what's possible with miniaturization.
It's fascinating how they managed to balance all these competing demands.
Right.
Miniaturization, power, efficiency.
It really is.
Yeah.
And that innovative spirit really comes through in their choice of materials, too.
Okay.
Like that special polymer
Right.
they used for the actuators, the one that allowed them to operate at lower voltages.
Right. Yeah. I remember thinking that was a pretty clever solution. It seems like they're constantly finding ways to optimize the design.
Exactly. They weren't afraid to experiment
Right.
with different materials and designs
Yeah.
to find the best possible solution for every challenge they encountered.
Free challenge.
And speaking of challenges,
Yeah.
making this robot truly autonomous was another major one.
Right. It's one thing to control it remotely. It's a whole other level to have it navigate,
Right.
make decisions on its own.
Exactly.
Yeah.
That's where those phototransistors came in.
Okay.
They act like the robot's eyes, allowing it to sense light
Okay.
and follow a light source.
So it's not just mimicking the movement of a flatworm. It's also responding to its environment
Yeah.
in a similar way.
Yeah, in a very almost biological way.
That's pretty cool.
Yeah.
Do you think this is a glimpse into the future of robotics, where robots can seamlessly blend in and interact with their surroundings, like living organisms?
It's certainly a step in that direction.
Yeah.
Imagine programming a swarm of these robots to follow a specific pattern of light.
Okay.
They could coordinate their movements, working together to accomplish a task.
Yeah.
The possibilities are endless.
It's almost poetic in a way.
Yeah.
A group of tiny robots inspired by nature, working in harmony to explore and understand the world around them.
I like that.
Yeah.
And it highlights a crucial point about this research. It's not just about the technical achievements.
Right.
It's about what those achievements can teach us about the natural world.
Right. It's like we're learning from nature to create technology that's not only functional, but also beautifully integrated with the environment.
Exactly.
Yeah.
But let's not forget about all the practical applications this research opens up.
Yeah. We talked about things like monitoring water quality, exploring delicate ecosystems, even assisting with search and rescue operations.
Exactly.
Yeah, those are some pretty amazing possibilities.
Yeah.
What other potential uses come to mind?
Well, think about industries like agriculture and aquaculture. Imagine using these robots to monitor crops for diseases, assess the health of fish populations, or even deliver targeted treatments or nutrients.
That would be a game changer for those industries.
Right.
Yeah, it could make them more efficient and sustainable.
Exactly.
Yeah.
And that's just scratching the surface.
Right.
There are countless ways this technology could be used to improve our lives and our interactions with the natural world.
It's truly inspiring to think about the potential.
Yeah.
And speaking of potential, I was particularly fascinated by that scaling analysis the researchers conducted.
Yeah.
You mentioned it briefly before, but could you explain what that involved and why it was so important?
The scaling analysis was a really clever way to optimize the robot's performance. They basically experimented with different fin sizes and robot lengths to find the perfect balance for maximum speed and thrust.
So they were essentially fine-tuning the design.
Right.
Based on the principles of fluid dynamics.
Exactly. They discovered that the optimal fin size is all about finding a sweet spot between maximizing surface area for propulsion and keeping the robot small enough to navigate tight spaces.
Tight spaces, yeah.
Think about how a fish's fin size relates to its body size.
Yeah.
That's essentially what they were studying.
That makes sense. So they were figuring out how to make the robot as efficient as possible while still keeping it small and maneuverable.
Precisely.
Yeah.
They also discovered that the robot's speed is affected by how quickly the fins undulate.
Okay.
They actually found a resonant frequency where the robot achieves maximum speed.
A resonant frequency.
Yeah.
So there's optimal speed at which the fins should move.
Exactly. And that optimal frequency changes depending on the size of the robot and the span of its fins. It's all about how the robot interacts with the water around it.
It's amazing how they were able to use both experiments and analytical modeling to understand these complex relationships.
It really showcases their deep understanding of both robotics and fluid dynamics. They weren't just building a cool robot. They were delving into the underlying science to make it as efficient and effective as possible.
It's a testament to the power of interdisciplinary research.
Absolutely.
Bringing together different fields to create something truly innovative.
I completely agree.
Yeah.
This research is a perfect example of how collaboration and a deep understanding of the natural world can lead to groundbreaking technological advancements.
And that's a great note to end on.
Yeah, absolutely.
For part 2 of our deep dive, we've explored the technical challenges, the ingenuity of the design, and the incredible potential this tiny robot holds.
It's been a fascinating journey so far.
Yeah.
And I can't wait to see what other insights we uncover in part 3.
Welcome back to the final part of our deep dive. We've covered so much ground already.
It's been quite a journey, hasn't it?
Yeah, from the tiny robot's incredible design
Right.
to the potential impact it could have on various industries. But what's even more exciting is that this research, it's just the beginning. It's a launch pad for even more innovation in the field of miniature robotics.
Absolutely.
Okay, so let's talk about the future. Where do we go from here?
Okay.
What are the next steps in the evolution of this tiny but mighty machine?
Well, the researchers themselves have highlighted several areas for further development.
Okay.
For example, one of the current limitations is the robot's operational time,
Right.
which is restricted by the capacity of its onboard battery.
That makes sense. Even with the most efficient design, a tiny battery can only hold so much power. So what are some potential solutions to this energy constraint?
Well, imagine if they could integrate energy harvesting technology, like a tiny solar panel on the robot's back.
So instead of relying solely on a battery, it could recharge itself using sunlight.
Exactly.
That would be incredible.
Yeah.
Potentially operate for much longer periods, maybe even indefinitely.
As long as it has access to light.
Exactly. That would be a game changer for applications like environmental monitoring, where you want the robot to operate autonomously for extended periods.
And speaking of autonomy, we talk about how this robot can already navigate by following a light source. But what if it could sense even more about its surroundings?
That's another area ripe for exploration, enhancing the robot's sensing capabilities. What if it could detect specific chemicals in the water? Or map the underwater terrain using sonar?
Wow, those are some really interesting ideas. It's like giving the robot a whole new set of senses to perceive the world around it.
With advanced sensors, these tiny robots could collect valuable data from environments that are currently very difficult or dangerous for humans to access. We could be on the verge of a whole new era of environmental monitoring and exploration. It's mind-boggling to think about the possibilities. Imagine a swarm of these robots, each equipped with specialized sensors, working together to create a detailed picture of a complex ecosystem.
They could monitor water quality in rivers and lakes, track the movements of marine animals, explore the depths of the ocean.
It really is endless.
Possibilities are endless.
And because they're so small and agile, they could access areas that are currently off limits to larger robots or even human divers.
Exactly.
They could weave through dense vegetation, navigate narrow underwater caves, or even slip through cracks in shipwrecks. It's like opening up a whole new world for scientific discovery.
I agree.
And we've only been talking about underwater applications.
Yeah.
Could this technology be adapted for use in other environments?
Absolutely. The principles behind this robot's design and locomotion could be applied to create miniature robots that can crawl, fly, or even burrow underground.
That's incredible. So we could have tiny robots exploring the rainforest canopy, navigating complex underground tunnels, or even helping with search and rescue operations in disaster zones. And don't forget about the potential for these robots to be used in healthcare. I remember reading about microbots being developed for targeted drug delivery and minimally invasive surgery. Could this research contribute to those advancements?
Absolutely. Imagine tiny robots that can deliver medication directly to a tumor site, repair damaged tissue from within, or even perform delicate surgical procedures with minimal invasiveness.
It sounds like science fiction, but it's becoming more and more real every day. It's inspiring to think about the positive impact this technology could have on human health. And it all comes back to that fundamental idea of bioinspiration. By studying and emulating nature, we can develop technologies that are not only incredibly functional, but also beautifully elegant and efficient.
I agree.
This tiny robot, inspired by a simple flatworm, is a perfect example of that.
It really is.
It's a testament to the power of human ingenuity and our ability to learn from the natural world. This deep dive has been a fascinating journey, and I think it's safe to say that this tiny robot is making some very big waves in the world of robotics.
I couldn't agree more. It's an exciting time to be following this field, and I can't wait to see what other innovations emerge in the years to come.
Thanks for joining us on this deep dive.
Yeah, it's been great.
It's been a pleasure exploring this incredible research with you. Until next time.